Yeah, do you see it now?
So you can use your...
Yeah, exactly. All right, so here's the deal. So it says, during a jump to his partner, an aerialist is to make a quadruple somersault lasting 1.87 seconds. So the time that he's going to be in the air for is 1.87 seconds. All right. It says, for the first and last quarter revolution, he's in the extended orientation. All right, so first quarter and last quarter. So, how do I want to write this? So, for 1/4 of a rotation, our I is the 19.9 kilogram meters squared.
That's only for rotation 1 and 4?
No, that's for the first 1/4 of a rotation.
Every single rotation? Because isn't it just when he lets
He's
go?
going to make 4 flips.
Right?
He's going to go around 4 times.
Right.
During the first 1/4.
Yeah, and then the last one.
Yeah, I just haven't gotten there yet.
Oh, okay, my bad. I'm sorry. I thought that we were...
Yeah. All right, and then in the middle, 3.5 rotations. Our I is the smaller number. He's tucked, 3.93 kilogram meters squared, right?
Yeah.
Follow? And then during the last quarter, we're back to 19.9, yes?
Yep.
All right, is everybody good at that?
Yep.
Okay. What is his angular speed? Let's see. During the rest of the flight with that, what is... okay. So, I'm looking at 2 different angular velocities, right? There's the angular velocity in the first and last part, and then there's the angular velocity during the tuck, right? So how do we want to distinguish between those? Does it call... I think this one is W2, right?
Yeah.
Is that right? Okay, so let's just call these W1 and W1, right? So, thoughts? Sure, Maggie, get me started.
I did a system of equations, and I got sort of...
My keyboard just perked up. So, talk to me about your system.
So I used the Hernandez equation using the delta theta and the second...
Gotcha. Did that work?
Like, I got maybe 0.1 off.
Okay, so here's my concern. So the Hernandez equation, this guy, I'm going to write it in linear form just because I am. That only works if you've got a constant acceleration. So is the acceleration going to be constant? So I think the way I interpreted this problem is this. Give me 1 second, Peter, and then I'll get you. All right. The way I interpreted it is that there's one time interval during which he's spinning at this angular velocity. Then there's an insignificant amount of time during which he tucks. So technically that's going to take time, but I think that the problem writers, are treating that as being 0 time. Okay? So then there's another chunk of time during which he's got this rotational inertia. Okay? Do you see where I'm going?
So you just use...
So what has to be true about these 3 times?
Oh, so...
Got it?
Delta x over t would be...
There you go. There you go. Okay. So Peter, you had your hand up very high in the air. What were you trying to say?
Well, I was because I agreed that, I use the system of equations too, except for that I, said that, okay, he needs to get through 4 revolutions in 1.87 seconds.
Yeah.
And so that was 13.44 radians per second on average, and then put an equation for average velocity.
Okay, yeah. Again, you can't do that because those average velocity equations only work if your acceleration is constant, and it's not. We're treating this problem as 3 chunks that are all constant velocity.
Okay.
There's a slow velocity, a quick velocity, and then a slow velocity. So it's like Roy drives at 10 miles an hour for an hour. Then he goes at 60 miles an hour for 3 hours. Then he goes at 10 miles an hour for an hour.
Yeah.
Okay, so we're not worried about the acceleration during those two spikes. We're assuming that's instantaneous. Okay, so let's do this. We know that our total time has got to be 1.87 seconds, right? So how can I write the time for one chunk? So we know that, so assuming your angular velocity is constant, we know that displacement is angular velocity times time. Do you guys agree with that? Assuming that your angular velocity is constant, which is what we are led to believe. During this chunk, he's going to have a constant angular velocity. During this chunk, constant. During this chunk, constant. So time is going to be delta theta over omega. So our delta theta is what? 2 pi over 4. So pi over 2 radians times omega 1. So that's time number 1, right?
Yeah.
Time 2 is what? 3.5 rotations. So 3.5 times 2 pi is what? 7 pi. Over omega 2. And then this is going to double it, right? So I basically need to double this, right? Follow? So that all needs to add up to 1.87. So I'm looking at pi over omega 1 plus 7 pi over omega 2 has got to add up to 1.87. So that's one of our equations.
All right. I got it.
Does that make sense?
Yeah.
Yeah.
Oh, and then you can do conservation of momentum.
And now you use conservation of momentum to get another equation.
Yeah.
So our other equation is going to be, let's see, 19.9 omega 1 equals 3.93 omega 2. So now I've got two equations, and you can solve the system.
How did you get that second equation?
It's just conservation of momentum. So this is the angular momentum when he's extended, right? Sorry. Right, here's our I, here's our omega.
Fine, right?
Good.
Yeah.
And then this is after he tucks.
Would you rather do an experiment or
Cool.
simulation?
All right.
Wrong answer. It's both.
Say it again, Molly.
Are we just looking at the first two parts? 'Cause, like, there's
So there's actually three. So there's the angular momentum before he tucks, angular momentum after he tucks, and then angular momentum after he untucks again.
right, so,
But untucks again is the same as pre-tucked.
okay, so that's why we don't have to look at it in that second.
Yeah, I mean, you could, if you wanted to, the third one would be just 19.9 omega 1 again.
Okay,
Do you know what I mean?
right.
So he's like, untucked, tucked, untucked, right? All three of those are equal. And the untucked and the untucked are literally equivalent. Follow, you guys?
Yep.
All right, problems with this.
No.
All right. One of the ones. A lot of you guys came in here like, this is really hard. So, and I don't mean that it wasn't, but where did we get
Oh,
tangled up?
sorry.
No, you're good. I just want to make sure that you're not monopolizing. Is anybody like, Peter?
I think a lot of people are like that, but just for various reasons.
Okay, yeah, sure, what do you got?
Alright, so this might have been really
How'd your
easy.
one plate go? The one I
So,
had
like,
last night.
If it was really easy, we don't need to do it, but can we do 18?